Okay, continuing on with 5.4, we're going to look at more log properties, and these are properties of the actual log terms themselves, how we can combine them. The properties are listed here, but I'd like to go through them one at a time, and we can see why we need them and how we can use them. If you remember, to solve log problems, often what you want to do is isolate the log term, and then take that base and apply it so that the base and the log of the base cancels. We'll see that in a minute. But anyways, the key here is isolate the log term. So when I look at a problem like this, I can't isolate the log term because there are two terms. So I need some way to combine those two terms into one term. And that's what these rules over here do if you look at them. This one's a little different. But these first two, you can combine log terms into one. So let's see how we can use that here. So what I want to do first then is get all the log terms on one side. So I can start trying to get things isolated. So I would add this whole term over here. And then let's move the 1 over on this side. All right, now I can use this rule. As long as the bases match, and the bases are 10 here, the sum of two logs, I multiply the arguments. So what we're going to have here then is log x times x minus 9 equals 1. Okay, now I have one log term, so now I can figure out how to get this out by itself, and our trick from last time was to raise each side by these powers and make the base match this base. So if this is base 10, I want 10 raised to this and 10 raised to this. When the base and the log with the same base match, they cancel, so that just leaves x times x minus 9. And over here on this side, 10 to the first power is 10. Multiply this, because what I'm going to need to do is expand this, set it equal to 0, find the zeros to get our solutions. So x squared minus 9x. Let's go ahead and minus the 10 over here. Kind of take an extra step there. Factor this. And then our potential solutions are 10 and minus 1. The reason I say potential is you need to go back to the original equation here and make sure that these work. And the only thing we're really looking for are you can't have the log of a negative number. So if I put a 10 in here, no problem. If I put a 10 in here, I still get a positive 1, that's fine. But as you can see, minus 1 gives a negative here and also a negative here. So we got to get rid of minus 1. So our solution is 10. Another thing you might notice here to help you kind of understand what's going on here, this is the inverse of the exponential function. And for the exponential function, when I had a base and it was multiplied by the same base raised to another power, what did we do with the bases? We added them. So you can kind of see it's similar here. When you're adding, you're multiplying. So that's kind of what's going on there. That's how these inverses work. Okay, for this one, I'm going to start off by using this rule backwards, and this is a good example because it shows that these rules don't have to work this way. You can also go from here to here, here to here. You can work them either way you need to. So, and the reason I'm going to take this product and split it up into two logs is because I noticed that if I had a natural log of 3, that's just a number. And I can find that on my calculator. So I'd like to split this up. So let's start there. And then a product can become a sum of two logs. So ln 3 plus ln x. So now what I would like to do is get all the logs over on one side and use one of these rules to combine them into one log and get all the numbers over on the other side by themselves. Well, these are just numbers. Again, you hit 6, you hit your ln key, you're going to get a number. Same with 3. So let me keep this one. This time I'm subtracting this from both sides. And I got my ln 3, and I'm going to subtract this. Okay, so this rule won't work now. I need a rule where I can combine two logs where it's subtraction. That would be here. I can combine them into a division. And if you think about this rule too, if I have a base raised to a power, same base in the numerator, I can turn that into what? The difference of the exponents. Same kind of thing going on here. When I'm dividing logs, that's the same as the difference. So they're, again, inverses of each other. Okay, so using this rule, if I want to combine these into one, I divide the first one by the second one. The order's important here. So ln x minus 1 over x equals, and then if I use my calculator here, and I'm just going to round maybe 4 places, ln 3, 1.0986 minus ln 6, 7918. Okay, so again, how do I get rid of this natural log so I can have just the argument? I use a base with the same power. Natural log is base e, so use base e for both sides. So e to this, e to this. These cancel. X minus 1 over x equals. And then if I add these together, that's going to be, or subtract them, e to the minus 0.6932. That's still a number. Hit E, enter this number, and it'll return 0.5 roughly. So x minus 1 over x equals 0.5. Multiply x over here. Okay. Then I've got 1x, and if I subtract 0.5x, that'll be 1 minus 0.5. That's 0.5x equals, add the 1 over here. Then if I divide both sides by 0.5, x equals 2. And 2 works anywhere here because it doesn't give you a negative. Okay, let's look at our final rule. This is an easy one. When you have an exponent on the argument here, you can leave it there or you can move it out front. You can leave it there or you can put it up here. You can move it. Okay, they're equivalent. So let's see how that works here. Okay, what I would like to do here, unfortunately, if I could make these bases the same, then I would be done. I just set these equal, but you're not going to be able to make 1/5 into 1/2. There's no way to do that. Okay, so I would like to get this out of there. So let's start by taking the log of both sides. Or I could use the natural log, it doesn't matter. So we're taking the log of both sides in this case. Now I'm going to use this rule, and I'm going to bring the power out front. I'm going to move it out front. So I'm going to move this here. And move this one out here. Now, these parentheses are important. If I don't put the parentheses there, it looks like x minus this log, but it's not. It's this whole thing times the log, so you got to be careful with the parentheses. Pretty much what we've always done, though. When you have a element and that whole thing is being considered, then you always put it in parentheses. Okay, good news. I can take the log of numbers and just use my calculator. So the first thing I want to do is let's go ahead and divide both sides by 3 over x. So we're going to divide this over here. And then I'll divide both sides by this one. Okay, I could even actually use this rule and combine these into a subtraction kind of thing, but I don't need to do that. Oh, not in this case. Okay, what I need to do here is simply up here I'd put in 0.5, I would hit the log key, and it's going to give me a number. Down here I'd enter 1/5 or 0.2, hit the log key, and it'll give me a number. So these are just numbers. Okay, hold on a minute, that looks like a 6. It's supposed to be an X. Okay, so again, if I put in 0.5, I'm going to get minus 0.301 rounded. And if I put in 0.2, I'll get minus 0.699 roughly. Okay, so let me put those here. So I have x minus 1 over 3 minus x equals negative 0.301 over negative 0.699. 2 negatives becomes a positive. So I can cross multiply here. Might have been easier to just put the numbers right here and multiply. It's hard to say. But anyways, if I cross multiply, this times this is 0.699x minus 0.699 equals, and then this one times this, 3 times 301.903 minus 301 times x. Okay, I'm going to add this x over here, and that's going to give me 1. So 6.99 plus 3.01 is actually 1, so that's just x equals. And then if I add this to 0.903, I'm going to get 1.602. And that's our answer. All right, these rules are great and we can use them. And if you notice here, everything here is in exponent form. Everything's here some sort of a log form. We're not mixing things. Sometimes that's okay. But let's look at this example here. Okay. This is typical. I have a mix of types. Okay, I have cube root here. It's basically an exponent. It's a 1/3 if you want to think of it that way. I have a log over here. Once in a while, if you're lucky, you can solve those kind of things, but generally, it's not going to be solvable. For example, I already know this log's isolated. To get rid of it, I would have to use e. So e to this power, e to this power. Then I could get the x plus 5 out. But then the problem is over here, the only way to get this x out of this exponent so I can solve for it, I would have to take the natural log of both sides. And let me put it in here, and look what happens. I'm back where I started. So there are a lot of problems, even with all the rules we have, and generally they're going to be of this mixed variety. They're not solvable analytically. That means with a paper and pencil. The way that these kinds of problems have to be solved, and there's some in your homework, but I didn't assign them because it just takes more technology. You really need to have maybe something like Mathematica where it'll actually just solve it with really weird algorithms. Or you can use graphing computers or calculators and hope that you can find the solutions. And I'll show you why I say hoping. First, your graph has to be really accurate, because if this equals this, that means we got the same x value. Well, this is the graph here of cube root of x. That's right out of chapter 3.1. It's the cube root function. This is the graph here of ln x plus 5 shifted to the log function shifted to the left 5 units, and it's going to go through some certain points. Instead of 1, 0, we'll have to shift back, so it'll go through minus 4, 0. Instead of 1b or e, we're going to have to shift that back, so those points are in here. That's a solution right there. And if you were really accurate, or you had a graphing calculator that could figure that out for you, that x value right there is minus 4.815 rounded. That's a solution. Hard to tell what's going on here, but believe it or not, the cube root function is rising a little bit faster than the natural log function here. So what's happening is eventually this one's going to pop up over the top of this one. They're going to cross. That's going to be your second solution. But it doesn't happen until you get clear out to 102.084. So somewhere way out here, these things actually cross. Once they cross, that's it. Because this will continue to grow at a faster rate than this one, so they'll never come back. So you would actually get two solutions. Again, you can read about it in the book if you want. There's a short section on it, and there are a couple of homework problems, but you would have to have a really good graphing calculator or other kind of software to figure these kinds of problems out. Okay, next time we'll wrap up 5.4. We're going to look at how to make base changes so that we can use our calculator to figure out some of these log problems where the base isn't e or 10. And then we'll solve an application using that.